at that. One second here, kids. All right, so here we go. I want to start looking at 3.8. We're getting down to it. We've had a lot of stuff in this chapter. This chapter's been kind of a long one here, and it's been, well, what's going on now? This does not want to work very well today. Okay, 3.8, title is Analyzing Graphs of Polynomial Functions. So we're going to be looking at a lot of things in Desmos today. All right, there's quite a bit of vocabulary that comes along with today, but I think that if you follow along and listen carefully, this will be pretty manageable. I think, like the last section, quite a bit easier in some of the stuff that we've looked at compared to rational root theorem and fundamental theorem of algebra, complex conjugates theorem, okay, irrational root theorem, okay. So 3.8, like I said, analyzing graphs of polynomial functions. Our question that we're trying to answer today is the following. We want to know, first of all, how many turning points can the graph of a polynomial function have, okay? When I talk turning points, it's basically like, how do you get to a maximum point and then start falling down? It's kind of like a roller coaster, okay? How many of you guys have been on a roller coaster? You get to this very top, it turns and starts going down. You get to the very bottom, and it might start going back up, okay? And we'll talk about those turning points. But in order to do this today, in order to ask how many questions or answer how many questions the polynomial function has in terms of turning points, we first of all need to be able to use what here, kids? Okay, you guys know what x-intercepts are. Use x-intercepts to graph polynomial functions. Okay. Second thing we're going to do is use the location principle, and we'll talk about this a little bit, to identify zeros of a polynomial function. We're going to find turning points and identify, this is kind of a biggie, local maximums and local minimums of graphs. We'll talk about what that means. And now we're going to lastly identify even and odd functions. Now, identifying even and odd function isn't as easy as just saying, ooh, the degree is 9, so it's odd, or the degree is 8, so it's even. It's not as easy as that. So there'll be some things that we look at that get a little complicated, but nothing impossible. All right? Okay, vocab. First of all, volunteer to read local maximum for me. You want to read that?
The y-coordinates of a turning point is a local maximum of the function where the point is higher than all the nearby points.
Okay, so if I had a graph that did this, okay, a local maximum would be like the peaks or the tops of a roller coaster, like when you get to the top part of a roller coaster. So how many local maximums does this graph appear to have, kids? Two of them, okay? A local maximum might be here and here, okay? So those points are higher, those 2 points are higher than some of the points around them, okay? They're like the peaks. I always call the local maximum, where are the peaks? Okay? So if local maximum is a peak, what do you think I might call local minimum? Anybody have a guess? Well, I call them the valleys, peaks and valleys, all right? So if I had the same graph kind of like this, a valley is like a part where the roller coaster gets to its lowest point, maybe going down and then coming back up. How many valleys are in this roller coaster right here, kids? There's 3. These 3 points would be my local minimums. Okay? All right. Even function, kids. I'm going to highlight some stuff. An even function occurs as a function f. It says it's even when f of negative x equals what? When f of negative x equals what?
X.
For for all x in its domain. So here's the deal. This is the part. If it's even, f of negative x would equal f of x. And we'll look at something like this in a little bit. Okay? Then an odd function says this. An odd function is an odd function when f of negative x equals what, kids? Oh, I keep covering that stuff up. It says when f of negative x equals what? Okay, and we'll look at some examples here in a little bit. All right, I'm not going to read through all this here. One thing I want you to underline here is this. If a function is even, it says it is symmetric about the what, kids?
Y-axis.
Okay. Even functions have a characteristic that look like this. I'm just going to draw a parabola right through the origin here. Okay? If I had to ask you guys to fold right there, fold that graph, where would you fold that so the left half fell on the right half? Well, you would say, Parson, we would fold that on which axis?
Y-axis.
Okay. So if you can fold anything over on the y-axis, if what's on the left mirrors what's on the right over the y-axis, then it's what type of a function, kids? Even. Okay? Then an odd function, it says right here, it says one way to recognize a graph that is symmetric about the origin is that it looks the same way after 180 degrees of rotation. So something that's going to be an odd function might look like this. Might come up here like so, down through here, like this. Now I didn't draw this the best, but kids, if I rotate it about the origin right here, if I rotated that about the origin half a turn, wouldn't that graph pretty much look exactly the same? In other words, if I could take this, well, maybe I can. Watch, let's see. Let me try this. Ooh. It's not going to be perfect, okay, but if I made half a turn with this graph, isn't it kind of the same? Then if I move it here a little bit again. Doesn't that look kind of the same right there? Okay, so you get what I'm doing there? Okay, so odd functions. Function is odd if you can rotate it 180 degrees about the, which point? Origin. Okay. End behavior we've talked about before. The end behavior of a polynomial function is the behavior of the graph as x approaches positive or negative infinity. Remember when at the very beginning of this chapter we said, hey, as x approaches positive infinity, y did something? Remember doing that stuff? And then same thing, as x approaches negative infinity, y was going to do stuff. That's all that end behavior stuff. So that's stuff that we've seen before. Okay? All right, so let's bump ahead to page 2 here. See what we can accomplish here. Bump ahead to page 2. Oh my gosh, there is more vocabulary. If a graph is increasing, the graph is increasing, what kind of slope will that part of the graph have? Okay, so I might say, ooh, part of a polynomial function with all the curves, I would say something like this. If this was part of a polynomial function, this graph from the point on the left to the right is doing what, kids? Is it increasing or decreasing? Okay? You always move left to right with increasing, decreasing. So an example of something that might be decreasing would look like this. Okay, this graph, as I move left to right, is going down. Okay? And then finally, symmetric about the y-axis. I kind of talked about that with the parabola. Symmetric about the y-axis means if you fold it on the y-axis, the left side would mirror the what? Left side would mirror the what? That would mirror the right at the y-axis, okay? So again, an example right here. We would say if I had a parabola like this, doesn't the left side mirror the right side right there? So I would say that that graph is symmetric about the y-axis, okay? All right, let's get into this here, kids. I want to talk about this idea of graphing some things and what it means. Okay, we'll talk about some fundamental stuff here. But example 1 says use what, kids? Use what? X-intercepts the graph of polynomial function. Now kids, here's the situation on this. We use x-intercepts, which are like roots, or they are like zeros, to find possible graphs of this. And how this works, kids, is we could come up with a chart. We could do this lots of different ways. But what I'm going to do is I'm going to look at these two factored parts right here, the x minus 2 and the x plus 3. So here's how this kind of works, kids. First of all, what value of x would go in here to make this 0? Positive 2. So right below it, I'm going to write positive 2. Okay? I also know that there's another set of parentheses or another factored part there that says x plus 3. Now this x plus 3, kids, what would go in there to make that 0? Negative 3. So I'm going to put negative 3 right below this. Now kids, I need you to be really careful. All right? There's kind of a rule right here, and I want to make a note about this. So I'm going to go ahead and write negative 3 is a double root, and let me tell you why. Okay? Guys, the x plus 3 part in parentheses, what power is right out there by it? What power is out there by the x plus 3? 2. If you ever have factored form like this, and you would have some kind of part in parentheses, in this case the x plus 3, you set that part in there equal to 0 to find your x value, but there's a squaring value out there. We say that that's called a double root. What that means, kids, is this. At negative 3, my graph is not going to cross from positive to negative or negative to positive. What's end up happening is this graph is going to come up, touch that point, and then stay on the same side of the x-axis. So it's kind of, this point might either be like a local minimum or a local maximum. Okay? A double root like this, when I have this power of 2 out here, is a double root. It's either going to be a local minimum or a local maximum. Okay? Now kids, the question becomes, how in the world do I graph this thing? Okay? Well, I know that one root is going to happen at negative 3. We know the other root's going to happen at what? 2. Okay, so I'm going to plot my two x-intercepts of negative 3 and positive 2. Now kids, I think the best thing to do here, I don't know if it's going to work or not. I don't know if the whole thing's going to fit the window. But I would say let's make a chart. Okay, I'm going to make an XY chart kind of like this. And I need your help. Okay, I'm going to go from, how many kids do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, beautiful. I'm going to start at negative 5 and go all the way up to positive 5. Okay, and here's what we're going to do. We're going to make a collection of points for this. Now, my table's not the best, and that's okay, but I need a volunteer to help me by putting negative 5 in for x right here. Let's just do the negative 5 together, kids. What's negative 5 minus 2 in this set of parentheses up here? Negative 7. Okay, bank that up here, negative 7. What's negative 5 plus 3, kids? 2. But 2 to the what power up here? So what's 2 squared? 4, right? 2 squared is 4. 4 times negative 7 would be negative 28. What's 1/4 of negative 28 now, finally? Or negative 28 divided by 4. Positive or negative? So when I input negative 5, what's my output, kids? So I'm going to go here left 5 and down 7. Turns out it's right about there. That's pretty good. Okay. What I need is your help. Gabriel, I'm going to have you put negative 4 in for me. Get an output. Annika, you've got negative 3. Xavier, you're responsible for negative 2. Maddie, you're responsible for negative 1. Okay. Sterling, you're the lucky one. You're responsible for 0. Jordan, you're responsible for 1. Keegan, you're responsible for 2. Rhett 3. Brandon 4. And Cade, you've got 5 there, okay? So tell me what your outputs are with those. Let's form a chart. When you've got a value, just raise your hand. Tell me what x value you had, and I'll get your output in there, okay? Got yours, Gabriel?
Yeah.
What'd you get?
Negative 1.5.
Negative 1.5. Right. Go ahead, Annika. What'd you have? Negative.
I don't know if I did it right. I got 0.
I like 0.
Okay.
Who was my negative 2? Yeah, David. Go ahead, Maddie.
I had negative 1 and I got negative 3.
Negative 1 is negative 3.
I was 3 and I got 1.
3 is 1.
Is that wrong?
I don't know. 3 would be 6, would be 36, 36. Wouldn't 3 plus 3 be 6 here?
Yeah.
6 squared would be 36, right? 36, what's 3 minus 2? 1. So 36 times 1 would be 36 divided by 4. Shouldn't it be 9, I think? You agree with that? I think 3 should be 9. 4 and 5 are going to get out of control, so let's go with 9. You all right? I think you used 12 in there or something like that.
Yeah.
Okay. You went 6 to the second power and called it 6 times 2 instead of 6. You make sense there? Okay. Who else?
For 0, I got negative 4.5.
0 is negative 4.5. Okay.
For 1, I got negative 4.
1 is negative 4. Squeezing these in there. Who was my 2?
Me.
You got 2 is 0. I like it because it should be 0. We already plotted that. How about negative 2? Negative 2 is negative 1. Okay. Yep, I like negative 1. Okay. 4 and 5, you guys are off the hook because it's not going to fit the graph. How's that sound? What did you have? Okay. So here's the deal. I'm going to plot these points. The first one I plotted was negative 5, negative 7. That's right about here. The next one I'm going to plot is negative 4, negative 1.5. So left 4, down 1.5. That's right about here. Okay. Then we had negative 3, 0 right here. We already plotted that because that was intercept. Next one's negative 2, negative 1, which is right there. We've got negative 1, negative 3 right about here. 0, negative 4.5. And then we have 1, negative 4, which is about here. 2, 0 up here, and then 3, 9 was going to be way up here somewhere. Guys, do we have enough points to go ahead and make a sketch of this graph? Okay, it's just going to kind of go like this.
Is that negative 4.5?
0, negative 4.5. Should be right about here, right?
No, what's the 3 after negative 4.5?
Negative 4, 0, and 9.
Okay.
Good with that? Yeah, I had to squeeze them in there. Sorry about that, Annika. Okay. So a good sketch of this graph would look like this. Now, if you wanted to know if you were kind of on the right track with the sketch of a graph, kids, where could you go to confirm that? Decimal, okay. By the way, what degree does this function appear to be? What's this? What kind of function looks like these sometimes when we graph them? It's kind of like a third degree function, isn't it? It has 2 bumps. We've got a degree 2 and a degree 1x right here, so this is actually a degree 3 function, okay? So sketching wise, kids, find your zeros first. Notice this right here. It comes up, it touches negative 3 right here, and then takes right off. This is a double root because right here at 0, does this graph cross the x-axis or just come up and touch it and stay on the same side of the x-axis? It just touches and stays on the same side. So when you see stuff like this, this is an example right here of a double, or we call it a double root. Sometimes we might call it a repeated solution, something like that. So right there, there's a double root taking place. Okay. All right, so let's move into example 2. Let's do some analyzing here. Instead of graphing stuff, let's analyze some things here. Example 2 says to do what, kids? Locate what? Okay, of a polynomial function. Okay, I can make you factor this, or I can make life kind of easy on you in this section. Okay, since we're looking at things graphically, I've told you to go where in the past? Okay, so let's load up decimals. You guys help me with the function. I'm going to type that in up here. So if you don't have your Chromebook open in front of you, you guys know where to go for that. But just pay attention up here today. Okay, kids, help me out. In in problem or example 2, what's the function that's given there, kiddos? What's the function they give us? Somebody read that in example 2.
F of x equals 4x to the third
It's 4x to the third.
plus 28x
28x squared,
to the second.
you said?
Yeah.
Okay.
Plus 21x
Plus 21x
minus 18.
minus 18. Okay, guys, when you graph this right here, it's saying find your what? Find your real zeros. Well, kids, right here, it kind of works out pretty nice for us. I'd say when you hit decimals right here, 1 0 happens at what value? 1/2. Another one is, and then where's the other one? -6. Okay. What degree was this function? What degree was this function? 3. So the most real numbers, or most real zeros we would have would be 3. Now keep in mind, could there be imaginary numbers here or imaginary roots? Well, absolutely there could be. Okay, so in this case right here, all 3 of them are real. So all you're going to say from example 2 is the following, kids. You would simply just say, well, from Desmos, our zeros are the following. What did we get again? Was it -6, -1.5, and what was the last one? 1/2? Okay. There's your graph again. Okay. I don't know how to make that much easier. Decimals is pretty magical stuff. Okay. It's the most beautiful graphing calculator in the world. Did you know that? You guys don't seem as excited about that as I am. Okay. Well, you know what? Let's run into this last page. Any questions so far? I know you guys are pretty quiet, but I think you're pretty on board right now. Yeah? Okay. Last page then. Let's rock this. Okay, there's some core concepts on this page. I need somebody to read that first core concept for me. Mr. Parson, would you read that for me? Why, sure, I'll read that for you, Mr. Parson. Okay, thank you, Mr. Parson. The turning points of polynomial functions. Okay, 1. The graph of every polynomial function of degree n has at most what? N minus 1 turning points. And then there's a second part to it. If a polynomial function has n distinct real zeros, then the graph has exactly n minus 1 turning points. Here's the deal. If I have a degree 17 function, okay, let's just say my degree is 17. As an example, let's say my degree is 17 here. So by number 1, it says the graph of every polynomial function of degree n has at most n minus 1 turning points, meaning 1 less than the degree. So what's the most number of turning points this graph could have? What's 1 less than 17? 16. Now it could have 16, but it can't have any more than that. It might have 14, it might have 12, it might have 1. It may not have a turning point. I don't know. Okay? But what this is saying is this. If I have a degree 17 function, then the most that you can have, 16, is the most, I'm going to abbreviate TP up here, most number of turning points it can have. That's what rule number 1 is saying about that core concept, about turning points of polynomial functions. The second one says if a polynomial has what? N what? N real zeros, then it has exactly n minus 1 turning points. So again, here's the deal. Suppose my function of degree 17 has 17 real zeros. So I would say 17 real zeros must mean then n minus 1 turning points. So if it did have 17 real zeros, then it would have how many turning points? Well, what's 1 less than 17? 16 turning points. So let's get into this idea. Okay, example 3 says find me some turning points. Example 3 says find me some turning points. Okay? Well, I say Parson, the turning point in the game was at 8:50 when the Hawkeyes went on an 8-0 run. That was a turning point, right? Or, when the Packers went 3 and out, and gave Russell Wilson a chance to go down and just score, that was a turn. Oh, never mind. Those are different turning points, aren't they? Find the x-intercepts, right up here in example 3, and the points where the, what's this say right here, kids? Local maximums and local minimums occur. Determine the intervals for which each function is increasing or decreasing. This is not too bad. Where do you think we're going to go for these, kids? Where do you think we're going to go for these? Yeah, let's throw it in decimals. Let's see what our graph looks like. So help me with this. We'll do the one on the left. So you guys tell me what I need to put in here. What's the function on the left there, kids?
X to the third power.
Okay, x to the third. All right, Sterling, carry on, bud.
Negative 2x to the second power.
Minus 2x to the second. Okay.
Plus x.
Plus x.
Minus 2.
Minus 2. Okay. Gosh, you guys. I'm going to zoom in a little bit. Looks like there's kind of a local maximum right in here and a minimum right here. If I was riding on a roller coaster, wouldn't this get to the top of a hill, come down a little bit, and then head back up? Okay, so let's take this. First of all, what degree is this?
Third.
Third. So at most, how many turning points? 2. Okay, our turning points are going to be, let me zoom in on this a bit. Our turning points are going to be basically, well, if I follow the graph here, one's going to be, oh, gosh, look what decimals even does for you. Don't they kind of get to the top of the roller coaster ride? Ooh, ha ha. They kind of give you those minimums and maximums, right? What's the x value for this turning point right here, kids?
Third.
1/3. What's the x value for this turning point? 1. Okay, so here's what I would say. Is this point at 1/3 going to be a local maximum or a local minimum? Is this a peak or a valley, honey?
Maximum.
It's a local max. This would be a local minimum. Okay, so we're going to go ahead in our notes and say, first of all, and I like to write this way. I say we have a local max. I just put L max like this at x equals 1/3. And then we have a local min at x equal, what was that value again, kids?
1.
1? Okay. And then it says determine the intervals for which each function is either increasing or decreasing. Okay, I think I can do that. I'm going to take a screenshot of this quickly. The stuff I'm going to write on this page, I want you to add into your notes in that same box, okay? So the box that you have right here, add into this, the stuff I write up here on the graph, okay? So let me do this quickly. Oh, I think this is what I need to do. Yep. Okay, kids, here's what we're going to do. We're going to say, first of all, these are my turning points here and here, aren't they, kids? Aren't those my turning points right there? So, guys, start at the far left of the graph. Is the graph increasing or decreasing to this first turning point?
Increasing.
It's increasing. So I'm going to say, first of all, the graph is increasing. And I'm going to write it this way. Okay, we're going to put a parenthesis over here. Now, if I would continue to go this way, isn't my x value going to continue to go to the left for this graph? I'm going to write it this way. For infinity, negative infinity, up to 1/3. Okay? This graph goes on down this way forever. It means it's going to go to the left forever. Okay? So the graph from negative infinity all the way over there, move it up this graph, up to here, increases from negative infinity until it gets to what value, kids? What value? Okay, get to 1/3. Then from 1/3 to 1, what happens, kids? Is it increasing or decreasing here? Okay, so we're going to say, you know what? This thing is decreasing from your x values of 1/3 to what? 1/3 to 1. Okay. Then, is it increasing anywhere else, kids? Well, yeah. Where does it start increasing again? After 1 all the way up to what? Infinity. It's not going to stop increasing. So the last part for increasing here, I could just add it with this one. I could say and from 1 to positive infinity, like that. Okay? So make sure you have that in your box there as well. Okay? Make sure you have that in your box as well. So I think a good thing to do would be this. I'm going to put the next graph up there for you. And I want you guys, first of all, to determine the local minimums and local maximums that are in the graph. And then I want you to tell me where the graph is increasing and decreasing. Again, decimals is pretty slick. They give you the x-intercepts, but what else do they give you on your graphs as well, kids? It's maximum and minimums or their turning points. Right? Guys, look at the next one in your notes there. What degree is that second example? 4. So at most, how many turning points will you have? How many? 3. At most 3 turning points. It's always a degree less than the degree of the function, or 1 less than a degree, if you will. Okay, so let's see what we can come up with here. So in example 3, we'll finish with this today and we'll call it a week right here. You guys read the function to me.
X to the 4th power.
Okay.
Minus 5x to the 3rd power. Plus 2x to the 2nd power.
Plus 2x squared, you said?
Yeah.
Okay, make sure I've got this right. Plus, okay.
Plus 8x minus 2.
What was the last value, Sterling? 2? Okay, so it looks to me, let me, I might have to zoom a little more on this one. Okay, there's a pretty good picture of it, okay? So the first thing we're going to do is find all of the turning points. You have to identify local mins and local maxes. So looks like to me this point would be what type of point right here, kids? Okay, so what was the degree of our function here again, kids?
4.
Degree 4. Okay. Degree 4 would mean at most how many turning points then? 3. And how many turning points did we identify here? Okay. So what I want you guys to do on your own, give this a shot, and we'll finish here today with this. Give it a shot. Write down, first of all, where your local minimums and local maximums are, what x values, and then tell me what intervals the graph is either increasing for or decreasing for. right, let's chat first of all, kids. How about local maximums first? What are the x values for local max? 1.07. Is that the only one? Okay. How about a local minimum? Or minimums, if you will. Okay. And 3.254. Okay. Are we good on the minimums and maximum parts of this? The turning points, if you will. Okay. Let's talk about increasing, decreasing. So let's start on the far left. Guys, is the graph increasing or decreasing to this first turning point? It's decreasing. So it's decreasing from negative infinity up to what point? So one way I can denote that is negative infinity to negative 0.574. Okay, and then from negative 0.574 up to 1.07, what happens? It's increasing. So I would put negative 0.574 to 1.07. It's increasing. Then what happens after 1.07? Decreases to where? So I'm going to have a decreasing from 1.07 to 3.254.
Then increase from 3.254 to positive infinity.
There you go, guys. Okay. Feel good about this. Enjoy your weekend, all right? Have your snow shovels ready for tomorrow, it sounds like. How many?
3 and 5.
Tonight?
Yep.
Sweet.